Hello there. I hope you are enjoying the course and you are finding the course useful too. It's important that you people give me a feedback. You see, what happens is when I teach this course in my classroom, all my students in the classroom have roughly same background, which means I know what they know, and from their feedback on the spot I can actually adjust my speed and make corrections in the course. But I assume that you all have probably different backgrounds, and some of you may be BSc students, some of you are MSc students and so on. So, it will be important if you give me feedback. It may be possible to do some corrections to the course. Okay, I might be able to add some extra material if you people want me to. Okay, so let's start with our third week. In the third week, what we are going to do is we are going to strengthen our ideas about Lagrangian formulation and also try to extend the Lagrangian formulation to some extent. Remember, we had written Lagrangian equations only for conservative forces and holonomic constraints till now. So, the first thing we will do is to extend this formalism to include forces which are not conservative, okay, or which cannot be put in a form of some sort of a standard potential. And also we will try to include non-holonomic constraints. Of course, not all possible constraints can be included, but remember the Pfaffian form that we had talked about. So, the constraints which are posed in that form we will try to include in the formalism, and after that of course we will do some examples which will sort of force our ideas or crystallize our ideas, and towards the end I will also include phase space, the notion of phase space. Okay, so let me begin by first incorporating what I call as velocity dependent forces. Okay, so to pose that problem, remember we start by talking about a system, and in the system we have n particles which have coordinates or position vectors given by r I, and then you have k holonomic constraints in the problem, and we know what we do in this case. We use these k holonomic constraints to reduce the degrees of freedom. That means eliminating k variables out of the problem, so that you have small n degrees of freedom, which is 3n minus k, and then this n dimensional accessible configuration space we will describe using generalized coordinates q1 to qn, and of course we have a transformation from q variables to the original position vectors. Okay. Now, in the derivation of the Lagrange's principle or Lagrange's equations, we started with D'Alembert's principle, and from there we added the generalized coordinates. Once we add generalized coordinates, we come to this equation. In this equation, on the left hand side you have a differential of T operator or kinetic energy operator, and on the right hand side you have all the forces there. Okay. And the right hand side contains only the non-constraint forces. Remember, we have already used the constraints, that means now we are not going to incorporate on the right hand side the constraint forces. Remember, the D'Alembert's principle tells us that the net work done by the constraint forces is 0, which means I do not have to consider those forces in my calculation. Okay. Now, here I can start making things special. Suppose all our forces are conservative. So, all forces are conservative. You remember what is the meaning of conservative? That means each one of these forces can be written in terms of some sort of a potential. So, I am going to write Fi, the force on ith particle. I should be able to derive it from some sort of a potential V, which is function of the n variables or 3n Cartesian coordinates. And here the gradient I refers to the gradient with respect to Ri. Okay. And if I have this situation, I can immediately calculate the generalized forces Qj. And remember, if you remember the derivation which we did in the first week, this is in fact nothing but del V by del Qj, and V here is of course function of then Q1 to Qn. Okay. And then we put this back into the first equation here, and when I put this back into that equation, what will happen is this. Remember, V, the potential, does not depend on the generalized velocities or velocities. So, that means partial derivative of V with Qj dot is 0, and this is what we used to write the final form of Lagrange's equations. So, d by dt of del Qj dot of t minus V minus partial of t minus V with respect to Qj, and this must be equal to 0, and this t minus V is what we call as Lagrangian. So, this was the derivation that we did in our first week. Now, the Lagrangian here, of course, what we have done in this case is we have considered a system where all the active forces or non-constraint forces can be written in terms of some potential. But then in the real system, of course, not all forces would be of that kind. There will be some forces, especially frictional forces or drag forces, you can't put those forces in this form. And when you can't put those forces in this form, how will I handle this? So, there are ways of doing that, and consider the next possibility where you see I have these forces. Do I need to write them as a differential or gradient of some potential? How about the notion of generalized potential? See, if you look at these equations very carefully, all that I really want is some potential here which gives me the generalized force by a definition like this. If it does, then I can still take the potential u to the left hand side of the equation and then calculate t minus u as the Lagrangian, and everything will be all right. Okay? But let me be more careful and also include the forces which are not of this kind or which cannot be put in this particular form. Okay? Remember, I have put this index C here, but that index C does not mean its conservative force. It is something that can be put in some sort of a generalized potential form. Okay? And this NC means I cannot put these forces in that particular form. Okay? Now, how am I going to handle this problem? So, what will happen is this. I will write this as, so we have d by dt q dot, and remember minus del q, which was equal to qj, and I will split this qj into two parts now. So, you have qjc and plus qj nc, and I know that qjc, now I can put it in a form which looks similar to the left hand side, and I will transfer that to the left hand side. So, this immediately gives us d by dt of qj dot of t minus u minus t minus u, this is equal to qj, those forces, those generalized forces which can't be put in the potential form. Okay, and then we will define this Lagrangian, which is T minus u. And remember, this u here is your generalized potential. It does not matter whether you can interpret this to be the energy of the system. We will not do that thing. Okay, all that we have is some sort of a generalized potential, which finally can be added or subtracted from the kinetic energy to define a Lagrangian, and from there we use Lagrange's equations to find the equation of motion. That was the agenda. So, this is what will happen if we have a problem where there are forces which can be derived from potential and forces which cannot be derived. So, forces which cannot be derived from potential will all appear here, and remember, all those forces which are like friction, which can be put, or also all those constraint forces which generate non-holonomic constraints. Remember, those forces also have to be accounted for. We have only taken care of the holonomic constraints, but non-holonomic constraints, those forces will also appear in this term here. Okay, fine. Now, we would like to ask this question. We have written some sort of a generalized potential here, but is that only an academic exercise? Are there actually forces which can be written in this form, or for those forces can we find a potential which has this form? And it turns out that in fact, one of the first or the most important force that we talk of in physics, which is the Lorentz force, the force on the charged particle, actually falls in this category. So, here take this as an example. We have one charged particle which is moving in an electromagnetic field, and on this charge then the force which is given by Lorentz force equation. So, this force will be equal to Q, which is charge of the particle, and E plus V cross B. Remember, this V here is nothing but the velocity of the particle. So, in the Cartesian coordinates, this V would simply be x dot, y dot and z dot. And how do we get electric and how do we describe electric and magnetic field? That of course is decided by the Maxwell's equation, and the most common form in which you represent these fields is the scalar potentials. So, electric field can be written as minus gradient of phi and minus del A by del T, and the magnetic field is nothing but curl of B. Okay. Remember, this is not electrostatics, but this is electrodynamics, which means electric field is not curl-less. The curl of electric field will be non-zero, in which case of course the description turns out to be in terms of both scalar field as well as the vector field. So, we have scalar field or scalar potential, which we denoted by phi. This is of course will be function of x, y, z and also t, and the vector potential which we denoted by A, that is also function of x, y, z and t. Okay. And then from this we want to calculate somehow the force equation or the net force on the particle. So, the claim that I am going to make is that the potential u can be written as, so this will of course be function of x, y, z, x dot, y dot, z dot and possibly also t. Okay. So, I will write this as function of r, r dot and possibly t as q times phi minus q times a dot v. Okay. And the claim we are making is that if this is u, then f is equal to, or I will just write the x component of this, f x will be equal to d by dt of del x over del x dot of u minus del u by del x. This will give you the correct form for the Lorentz force, which means this should be equal to q times x component of E plus x component of V cross B, and this is what we are looking for. Let us do this calculation, it is very straightforward. So, I will start with first. So, if I calculate del over del x dot of u, remember u has q phi. So, this is nothing but q phi, remember phi is only function of x, y, z and t, minus q times this has a x x dot plus a y y dot and plus a z z dot. So, the only way that it depends on x dot is only through this term, and remember both phi and a, all three components of a, they are all independent of x dot, y dot and z dot. So, this in fact will simply be equal to minus q times a x, and then we want to take one total derivative with respect to time. So, d by dt of del x dot of u, this is nothing but minus q times, and remember it is a total time derivative, which means I should take a x with respect to x into x dot plus with respect to y into y dot and plus the partial derivative of x with respect to z into z dot and plus it may depend on time too explicitly, which means there will be a term del a over del t. Okay. And the second term that we are looking for, which is minus of del over del x of u, and this will be equal to minus q times, I will write everything inside the bracket. So, this is del phi by del x minus, and now we will take derivative of all these ax, ay, az with respect to x. So, that would be del of ax with respect to x into x dot minus a y with respect to x into y dot and minus z with respect to x into z dot, and then we want to put these two together, and you can immediately see that the term here, this term would cancel with this term. Okay. And what you are left with is, so I am basically adding this equation and this equation together. Okay. So, what you are left with is minus q times, so I will take this minus sign inside. So, that is minus del phi by del x, okay. And then I will put this term also along with this del a by del t, and plus you have collect the term in y dot. So, you have y dot into, so there is a positive sign here, del a y by del x minus del a x by del y, and plus one more term which is in z dot, which is del Az by del x minus del Ax by del z. Okay. And now you start identify various terms there. Can you see that this is nothing but E of x, and then this term here is nothing but Bz. This one here is nothing but minus of By. Can you see that? You can get this from here. Bz will be equal to, when you take curl of B, that would be derivative of By with respect to x minus derivative with respect to y of Bx. Well, that's exactly the term that you have here. Okay. And then finally, what you are left with is the exact form of the Lorentz force. So, there is at least one example which fits the description we just now discussed of the generalized potentials. So, if you find any other potential which after this operator gives you correct form of the force, we can of course include that in the Lagrangian instead of keeping it on the right hand side as a force. Fine. Here is one more example. The more common forces, the drag forces, the frictional forces, you know that these forces also depend on the velocity. In fact, the typical form of such force is this: the x component of a drag force. So, frictional force, or I will just put F for friction, but it could be any kind of drag force. Typically, these forces are of the form x dot. Remember the Stokes law for spherical particles in the viscous medium? That is exactly what this is. Okay. And then similarly, you have y component and the z component. Okay. Now, how to treat these kind of forces? There is again a simple idea. So, this I will write it as minus Vx, V being the velocity and x component there. Okay. But you can see I can easily write this as, so, as minus derivative with respect to x dot, that is Vx, and inside I will write this as half kx and x dot square. Okay. Now, I will add the remaining two and write the net frictional force, all three components put together will be minus gradient of half kx x dot square plus half ky y dot square plus half z dot square, but the gradient is not with respect to the coordinates, but it is with respect to the velocities. Okay. So, this is basically gradient with respect to velocities there, and this quantity here inside the bracket is called as Rayleigh's dissipation function, and that actually indicates if this force is present, it will also do the work and extract the energy from the system, or the energy of the system will be dissipated through this force, and that is why this is called as Rayleigh's dissipation function. And you can also put this in terms of the generalized coordinates, in which case the corresponding q f j, in fact you can see that this is very easy, that it will turn out to be minus del f, I will denote this by curly f, del of curly f with respect to qj dot. Okay. Put this back into the Lagrangian. So, if in the Lagrangian equation, so if you have these kind of forces present, then you have del qj dot minus qj, and on the right hand side you have qj dot. Okay. So, what does the Lagrangian contain? All those forces which can be derived from some sort of a generalized potential, they all go to the left side and become part of the Lagrangian function, and the dissipation functions or the drag forces will be introduced through the Rayleigh's dissipation function. So, even in this way we can take care of the velocity dependent potentials. What if there are more forces present? Of course, remember that this is not the end of the story, but if there are dissipative forces which can be described by Rayleigh's dissipation formula, there are forces which can be described using generalized potential, all these will come here, and in addition to that, if there are more forces which cannot be put in either of these two forms, of course, I will have to retain those as it is, and I will again call that as QNC, but basically what we mean is that I cannot put these forces in any of the forms which I have already considered. Okay. So, this is how you take care of more general formalism or forces which can be put in a more general form. Okay. Now, what I am going to do is we are going to extend this formalism. We have already extended it to include some additional forces or categorizing different kinds of forces, but now I am going to add the non-holonomic constraints in the problem and describe how to take care of this non-holonomic constraint. But before that, let me describe this. Even if you have holonomic constraints in the problem, remember what happens. Each of these holonomic constraint is supposed to reduce the number of independent variables by 1, which requires you to do some sort of a elimination process using this constraint equation. But you see, in theory it is possible, in practice you may not actually be able to do it. The equations could be pretty complex, and if they are complex, you may not be able to take one of the variables to the left hand side and write it as a function of remaining variables. And if you can't do that, then how would I choose my generalized coordinates? That won't be possible. So, even if you have L holonomic constraints, maybe not all of those are usable. Okay. So, first what I will do is I will describe how to take care of this situation, and then the generalization to non-holonomic constraint will be straightforward. And this particular case where we cannot treat certain constraints either holonomic or non-holonomic will require you to use what is called as a Lagrange's lambda method or Lagrange's method of undetermined coefficients. So, before going to the actual non-holonomic constraint systems, I will first describe the Lagrange's lambda method. The Lagrange's method of undetermined coefficients basically is aimed at solving or finding the extremum of the functions where there are constraints. That means the function is defined over a domain, but then we do not want minimum over the entire domain. There is a constraint, that means which isolates certain amount of region from the domain, and in this domain we want to find out where the minimum or maximum or extremum point of the function lies. So, here let me first consider a standard problem of minimization. In the standard problem of minimization, we have a scalar function which is defined over R n, which means it is function of n coordinates. So, given function of x n coordinates, I want to find the minimum of this, and remember we have done this earlier too. In that case, the variation in the function, when I vary the coordinates about a point, if that variation is 0, then we say it is a stationary point, and we know that the stationary points are either minima or maxima, or probably some other combinations of this like saddle points. Okay. So, what we are looking for is this: the change in the function will be given by sum over I del f over del xi into dxi, and this must be 0 at some point x bar, then the x bar point is a stationary point. Okay. So, f has a stationary point at x bar if df is equal to 0. Remember, this must be true for all possible variations in all directions. Remember, we have discussed this when we were doing the variational method, and which means all these variables xi must be independent of each other, so that the variations in them are also independent of each other, and hence this would be 0 only if del f over del xi is 0 for all I. For each variable, the partial derivative must be 0, and that is when you get the stationary point. Here is a simple example. So, this is a function which is x square plus y square plus 1, and the graph is shown there. From the graph, we can immediately see that the minimum lies at x is equal to 0 and y is equal to 0. Now, we can of course use the formalism we have just now talked about. So, if I calculate the partial derivative of f with respect to x, that would give me 2x, this must be equal to 0, and the partial derivative with respect to y also must be 0, and this gives me the point where the function has minimum, and the minimum value of the function here would be 1. Okay. Now, let us go to the constraint problem. So, now we have the same function which is defined over Rn, but we want its minimum or extremum which is subject to a constraint like this. Okay. Here is an example, and this is what we are looking for. So, in the same example where function is x square plus y square plus 1, remember this has a minimum at the origin, that is x is equal to 0 and y is equal to 0, but we do not want that minimum. We want a minimum on the domain or on the line which is given by this equation x plus y minus 1 is equal to 0, and you can see that I have drawn that line there. So, this is your x plus y minus 1 is equal to 0 line, and now we have a restriction of the function on this line, which I will show by drawing a vertical plane over this line, and wherever this plane cuts your original graph, this is where you have a restriction. Okay. And in this restriction, where is the minimum is a question, and in fact that minimum happens to be here. When you drop that or take its inverse image into the domain, we know that this function has a minimum at x is equal to half and y is equal to half. Okay. Remember, the global minimum is somewhere else, but we are looking for a minimum under this constraint, and the meaning of that is I basically look at the restriction of this function on this domain described by this function there. Okay. And how to handle this kind of problem? Here of course, you see just taking derivative with respect to x and derivative with respect to y and equating it to 0 will not work, because that will again give us the global minimum. That will not give us the minimum that we want here in this constraint problem. Okay. So, there are two ways of handling this problem. Let me start by the first method. In the first method, which is exactly what we did for our holonomic constraints, you see the domain described by g is equal to 0 is in fact a line. It is one dimensional domain, okay, or a domain which can be described using one independent variable. And then all I have to do is I get rid of the dependent variable, reduce this problem to a problem of a function of one variable, and then the minimum can be found. Okay. So, let us do that. So, from the constraint equation, I am of course free to choose my generalized coordinates. So, I am going to do something like this. I am going to choose x is equal to half plus t and choose y is equal to half minus t, and where t of course is some real number. So, as t goes from minus into plus infinity, you get points of this line. Okay. Now, put that back into the function. Sorry, there is a mistake here. I will add that plus 1 here. Okay. So, now let me put this here. So, your f now can be defined as a function of single variable t, which is basically function f of x and y, and immediately this would become half plus t whole square plus half minus t whole square and plus 1, and this of course will simplify to 3 by 2 plus 2 times t square. Okay. And if I plot this function, you can immediately see, if I plot this as a function of t, then this f tilde is nothing but a parabola passing through 0, 3 by 2 point. And from the graph it is very clear that the minimum is at 0, t is equal to 0 and its value is 3 by 2. But we of course use the standard calculus to do this. df tilde by dt must be 0 for a minimum, and this immediately tells us that 4 times t must be equal to 0, giving you the answer t is equal to 0. Okay. This is one way of solving this problem. But you see, this is exactly same as what we did in case of holonomic constraints. We had the original problem and we have constraints, and once we have constraints, we got rid of as many variables as we could through each of those constraint equations. Okay. And in theory of course, we will assume that we can use all the constraints, but in principle or in practice it may not be possible. Okay. Here is the second way of doing things. So, the same function, same example, if I look at what I have plotted here in this graph is, this is your x axis, this is your y axis. The red line here is in fact the line x plus y minus 1 is equal to 0. Okay. And the blue circles which I have plotted here, they are basically f is equal to constant surfaces. Now, when you have f is equal to constant surfaces, we call them as level sets of f. So, you have level sets of f which are given by f is equal to some constant line. Okay. And what we want is the minimum as we travel on the red line. And remember, in fact, this particular equation g is equal to 0 gives me the straight line, but remember this straight line also can be thought of as one of the family G is equal to C. G is equal to C also will give you level curves, and in this case what those level curves would be? They would be lines which are parallel to the red line which is here. And when we want a minimum as we travel along the red line, is at this point the variation in the function must become 0. What does that mean? That means your level set of f and level set of G must be parallel here, or in other words the normal to both these given by this arrow here. So, the normal to the level set of f must be parallel to the normal of level set of G, okay? And that I will write here. We know that the normals can be obtained by using gradients. So, gradient of f must be parallel to gradient of G, and because they are parallel, of course their magnitudes may not match, but the directions must match. So, I will put one extra lambda there. Okay. This lambda we do not know to begin with. So, let us write this again as f minus lambda G, this must be equal to 0. And if I write it in terms of, for a more general situation, if f was a function from Rn to R and G is also some constraint defined over Rn R, in which case you can think of f minus lambda G as a new function h, and all that we are trying to do now is trying to find the minimum of this function h using a standard procedure. This is exactly what we do when we have a standard minimization problem. Now, here must be 0. So, the partial derivative of h with respect to xi must be 0 for every xi. What has happened here? By you see, the function h is actually not fully known. In the function h, there is one unknown variable, that is lambda. So, how would I get lambda? What I would do is I would find this solution. This gives me all the xi star where the minimum occurs, minimum of h occurs, but remember that undetermined lambda would still be there. Okay. So, basically you obtain xi star where all the partial derivatives are 0, but the xi stars would be in terms of lambda. And how do I determine lambda? Go back to G is equal to 0. This will give you value of lambda finally. So, what did we do? We in fact reduced the problem as if it was not a constraint problem, but a normal problem, normal minimization problem. And in this problem, we have inserted one unknown variable which must be determined finally using the constraint equation itself. Okay. What is the price to pay? When I eliminated a variable, if I started with n variable, I eliminate one variable because I had one constraint, I get n minus 1 variable. Like in this example, we started with 2 variables, use the constraint and gotten rid of one variable, or in other words I used one generalized variable t instead of 2 variables. But now in this problem I have n equations here and one more equation here. So, in principle the price that we pay is we have n plus 1 unknowns, which are x1 star to xn star, which is what we have to determine, and we also have to determine lambda. And then how many equations we have? n plus 1 equations. We also have n plus 1 equations. Okay. This is how we can get the minimum in the constraint problem. Let us apply this to the example at hand. So, for this problem, okay, so your g is x plus y minus 1. Okay. Let us construct the function h. Function h will be equal to x square plus y square plus 1 and minus, you have lambda times, so lambda x minus lambda y minus lambda. Okay. Then the two equations we get are, which is 2x minus lambda, this must be equal to 0, and 2y minus lambda, this must be equal to 0. And you see, when I solve this, I get x is lambda by 2 and y also equal to lambda by 2. So, I have got these minimum positions, but in terms of lambda. And then how would I, so I will call this as x star y star. And how would I get lambda? Because I have constraint g must be equal to 0. This implies that x star plus y star minus 1 is equal to 0, and this immediately gives you lambda by 2 plus another lambda by 2, that will be lambda, and lambda must be equal to 1, and this completes the solution. This immediately gives x star is equal to half and y star is equal to half. So, this is how we do the program of. Now, the extension of this to many variables would be straightforward. So, if I want to extend this method to many variables, then, so you start the same problem, you have function f which is function of n variables. We want to find the extremum of this function, and we have constraints in the form of these functions, but now you have k of these constraints. So, I goes from 1 to k. Okay. So, you have k constraints there. I will leave it to you people to figure out the proof, but all that we have to do is construct a new function which will be equal to f minus sum over I lambda I g I, and then find the minima of h. These minima will be in terms of lambda i's, and then you get lambda i's from the constraint equations themselves. Okay. In this case, of course, the minimization condition would be again is equal to 0, and this looks like a normal problem. You don't have to worry about the variations being independent of each other. You just think of this as a standard minimization problem where all the variables are independent, and these are n equations, and plus you have k equations here. And how many unknowns you are determining? So, you have n plus k equations and also n plus k unknowns, out of which n are your variables, n variables are x1 to xn, and remaining k variables are lambda 1 to lambda k. Okay. So, this is the program we want to employ to our non-holonomic systems. But of course, remember this problem where you have undetermined values of lambda, that does not mean that there is a unique set of lambda values which will give you the minimum. Okay. And there need not even be a one minimum. I keep saying minimum, but what I really mean is a stationary point. there could be a minimum and a maximum in the problem, in which case you get two solutions. I'll just give you one example, which is in fact similar to the one which we did earlier. Say in this example, the function f is given by -1. Okay, this is the function we want to minimize, and the constraint is in fact g function of x and y, which is x square plus y square is equal to, I will put it as 1. Okay. Now, what will happen is this. I will of course ask you people to solve this problem, but I am going to show you what will happen in this case. Here, how do the level sets of f look like? The level sets of f look like this. They are given by, okay, they are given by x plus y is equal to some constant plus 1 equations. Now, how does the constraint look like? Your constraint is in fact a circle. So, the constraint is in the form of a circle, and now you see what happens. The level sets of f are actually tangential or parallel to level set of g at least 2 points. That one is a point here and there is another point here. And if you look at the function, you will immediately see that the value here of the function is larger than the value here. So, over red line, as you go from point A to point B, from either side the value of the function is increasing towards B. What we get is a minimum value of f at A and maximum value of f at B. Okay. So, when you actually solve this problem, that is find x star y star in terms of lambda and put it back into the constraint equation, but the constraint equation is quadratic, which means you actually are going to get an equation in lambda square. When you solve it, you get two values of lambda and hence two solutions. So, given a problem, of course, the lambdas may not be uniquely determined, not one of them, in fact, there may be more than two solutions and all of those will be stationary points, but some of them will be minima, some of them will be maxima, and some of them will be saddle points. Okay. Now, I want to apply this to our standard Hamilton's principle. Okay. Now, let us apply this method to the Hamilton's principle. Okay. Let me first start by just considering holonomic constraints. Okay. Let us start by considering a system with capital N particles, then you have 3n coordinates, and let me say there are L holonomic constraints. Okay. Now, normal procedure would be I somehow use these L holonomic constraints and reduce the number of independent variables to 3n minus L. Okay. And why not? If possible, I should do that. And again, as I discussed earlier, it probably may not be always possible. So, let me assume, let me start by writing things down. So, we had n particles and L holonomic constraints. Okay. So, the net degrees of freedom would have been, so would have been 3n minus L, okay, and I would have used 3n minus L generalized coordinates. But now I am going to say that out of these I can use only L1 holonomic constraints to reduce the degrees of freedom. Okay. So, out of these L1 are some sort of usable and L2 I cannot use. Okay. So, these are also holonomic constraints, but not useful. Not useful means I cannot use these equations to reduce the number of variables, or I cannot find a set of generalized coordinates which will include this. Okay. So, the number of generalized coordinates in this case will be n, and that will be equal to 3n minus L1. Okay. So, I managed to use these many, and let us call these by q1 to qn. Okay. So, I am using these many generalized coordinates, and now the remaining ones. So, remaining L2 holonomic constraints, they are over and above these n coordinates. Okay. So, they are written in terms of Fi, which is function of q is equal to some constant, or I will put that as 0, and I here goes from 1 to L2. Okay. So, now we have a problem where we already have generalized coordinates which are n in number, and in addition now I have further L2 constraints. Okay. So, all these coordinates here, they are not independent of each other. There are some constraints which we have not used, and they will in fact bind or relate these coordinates there. Now, let us get back to our action principle. The problem reduces to minimizing the action. So, here J, which is written as Q, okay. Remember the Q variables here. So, Q n variables here, which is integral from T1 to T2, the Lagrangian, which is function of q dot t dt. Okay. And to find the stationary points of this, we look at the variation, and when we calculated the variation in J, remember all that standard procedure will apply. We have to make virtual displacements and construct new paths, and when we do that, this will reduce to, so the variation becomes delta J will be equal to integral from T1 to T2, and remember what did this come to? This came to d by dt of del L by del Qi dot minus multiplied by delta of Qi dt and summed over all I. Okay. This is what this is the equation that we get. And what do we do at this point? We say we want the stationary point of J, that means the variation must be 0, and at this point if we had only holonomic constraint and all those holonomic constraints have been used and we do not have this additional constraints there, in that case of course this delta Qi's will be independent of each other, and you can use that fact to set each of these brackets to 0. and that is how we got the Lagrange's equations. But now the minimization problem is a constraint problem, because I want variation in J, but all delta Qi's are not independent because they are related by these constraint equations. So, if I want to write that constraint equation in the form of, so also function of possibility, if I want to write it in terms of the displacements or infinitesimals, then the constraint equations will look like, so we can write it as sum over I b j I into dqi plus bj is equal to dt is equal to 0. Okay. And this of course automatically means that your bji must be equal to partial derivative of fj with respect to qi. And what must be bj? Bj must be equal to partial derivative of fj with respect to t. And once we have this form, remember we want to use what we called as virtual displacement, not actual displacement. So, virtual displacements will satisfy which equation? Virtual displacements satisfy this equation, bji times delta qi, this must be equal to 0. And remember j goes from 1 to L2. Now, use the Lagrange's method. This is exactly what we had in case of Lagrange's problem, Lagrange's method of undetermined coefficients. So, what I need to do is, now I should treat this as a standard minimization problem in n variables and plus additional L2 undetermined variables. So, write this as delta j is equal to sum over I integral from t1 to t2, and this bracket as it is q I dot minus partial derivative of L with respect to qi, and multiply these equations, each of these equations by a lambda j and add it to this problem. So, minus summation over j lambda j into bji, okay, multiplied by delta qi, and this must be equal to 0. And now this, according to the Lagrange's method, this is a standard minimization problem. So, each of these individual brackets must be 0. This tells us that the Lagrange's equations in the presence of additional constraints would reduce to this, qj must be equal to sum over j, sorry, I made a mistake in the, so this is I lambda j bji, okay, and remember I goes from 1 to n, so there are n equations in this, and this j of course goes from 1 to L2. So, there we solve these equations and we get q's in terms of undetermined lambdas. How do I determine those lambdas? I go back to your constraint equations there. If you go back to your constraint equations, you can of course immediately calculate the lambdas. So, this is how you incorporate the holonomic constraints which you cannot use to determine the set of generalized coordinates. But now something nice happens. Look at the form of these holonomic constraints. While deriving this equation here, this one, the form of constraint that I used was not really the original form which is given by this, but the differential form which is given by this here. Okay. But that is nothing but given in Pfaffian form. How does it matter now at this point whether that Pfaffian form of constraint is integrable or not integrable? You see, you can actually incorporate non-holonomic constraints just like we incorporated holonomic constraints here. This is how we would treat non-holonomic constraints in all the problems that we get. And in fact, this is not very difficult to see. Again, the price that we pay is, if I had used all the constraints, what would I be solving? I would be solving n minus L, or same as n minus L1 minus L2 equations in those many unknowns, and those are of course generalized coordinates. This is if I use all constraints. But what we have done in this particular derivation is we have used only L1 constraints, and the remaining ones have been introduced using Lagrange's lambda multiplier method. So, how many equations am I going to solve now? I am going to actually solve n minus L1 Lagrange's equations plus L2 constraint equations. And how many unknowns? Again, you have n plus L2 constraint, L2 unknowns there. So, this is n minus L1 plus L2 unknowns in the problem. So, this is a very elegant way of actually incorporating non-holonomic constraint, but remember, these non-holonomic constraints are not in the general form, but only in Pfaffian form. If you want to know how you can take care of more general set of non-holonomic constraint, Goldstein's book actually mentions this. It is based on a paper written in 1966 in American Journal of Physics by Ray, and on the basis of that he has shown a derivation where you can take care of very general form of constraints which are non-holonomic. But of course, for this course I will not touch that part. Those who are interested, I will ask them to look at the Goldstein's book. Here we of course have taken care of some of the issues of non-holonomic constraints, that is the non-holonomic constraints which are in a specific form or in a restricted form as they call it in Goldstein's book.